Welcome to Process Dynamic Control lecture series. In my previous lecture, I discussed about the leg in the distillation column. That means mainly we discussed about the three types of leg. First one is leg in the liquid. Then we discussed about the vapor leg. And third one we discussed about the concentration leg. Now, in this lecture, we will discuss about the frequency response of column. And then after we discuss about the last topic of this chapter is the predicting the behavior of control system. So here, this is the last lecture for this chapter. So in this lecture, we discuss mainly two topics. First one is the frequency response of the column. And then we discuss about the predicting the behavior of control system. So now we start with the frequency response of the column. So here we understand the importance of frequency response in the column. So now we start. The exact solution for frequency response of a column are just as difficult to obtain as the transient response, even after linearizing all the equations and treating the concentration and flow leg separate. So the frequency response getting is as difficult as the transient response. So the problem is to obtain the effective concentration leg, which are root of the nth order equation. So this is the main problem to obtaining the frequency response of this column. For particular cases, the linearization equations can be solved by standard procedure, or a digital computer can be used to calculate the transient for the either open or closed loop behavior. So here we can use the linearization equation can be solved here by using the standard procedure, or here in the latest technology we use the computer to solve the linearized equation. Consider the most common control scheme, which is involve varying the reflux to keep a constant composition on the top plate or a plate near the top. If the control point is end plates from the top, there will be n-1 liquid flow legs in the control loop, each of which can contribute up to the 90-degree phase change. So here we understand, if in the control point in the end plate from the top there will be n-1 liquid flow leg in the control loop, and each of that can contribute up to the 90-degree phase change. Following the suggestion of Armstrong and Wood, this leg can be considered to act in series with the concentration leg that would exist if there were no flow legs. It seems logical to expect the major concentration leg to be the same as that for the transient response. Like column capacity divided by the flow rate. As per the proof of transfer function for the 4-plate column are given in my next example. So we understand by using the transient response by using this example. So here consider this is the figure for this example. So the transfer function for 4-plate column basis liquid feed at the boiling point is dy by dx is equals to 1 for all plate. Negligible low leaks here, and F is equals to 1, D is equals to 1, B is equals to 1, V is equals to 3, and R is given equals to 2 moles per unit. That means moles per minute. This is the symbol unit for the F, D, B, V, and R. Same as here H1, H2, H3, and H4. The value is 1 mole per plate. So in the figure you can consider there is a 4 plate, and for the different value of the the value of H1, H2, H3 and H4 here is the same 1 mole per minute. Now if the both reflux rate and the feed composition are considered as variable, that means here we consider the reflux rate and the feed composition are variable. The 4 basic equations are: first one is H1 into S plus R plus D into X1 is equals to V X2 plus delta R XD minus X1. Second one equation is H2S plus R plus D into X2 is equals to Vx2 plus Rx1 plus delta R X1 minus X2. Third one equation is H3S plus R plus F plus D is equals into X3 is equals to Vx4 plus Rx2 plus Fxf plus delta R X2 minus X2. And the last one equation is S4S plus B plus V into X4 is equals to R plus F into X3 plus delta R X3 minus X2. The terms X1, X2 up to X4 represent the deviation from the normal value, which are X1, X2, small x1, small x2. Now, for the specific flow chosen, the transfer function for the changes in the feed composition are, that means the ratio of X1 by Xf is equals to 0.25s plus 1 upon 1.82s plus 1, 0.46s plus 1, 0.17s plus 1 and 0.097s. Same as for the X2 by Xf, we can write as 0.25s plus 1 into 0.33s plus 1 upon 1.82s plus 1, 0.46s plus 1, 0.17s plus 1 into 0.097s plus 1. Same as we can write the transfer function for the change in reflux rate are x1 upon delta. So the value is 0.23x into 0.41s plus 1, 0.18s plus 1 into 0.95s plus 1 upon 1.82s plus 1, 0.46s plus 1, 0.17s plus 1, 0.09s. Same as for the x2 by delta R, the transfer function for the change in reflex rate is given as 0.20 upon 0.03s plus 1 upon 1.82s plus 1. And x1 by delta R we can write as 0.2446 upon 1.82s plus. The last example we discussed in my previous slide for the change in feed composition, which are one of the most important load changes. The top plate response is somewhat slower than the response of the second plate, though both are dominated by the major time constant of 1.82 minute, which is quite close to the 2.0, the total boilup divided by the feed rate. For the change in reflux rate, the response of plate 1 has maximum lag of 90 degrees, and the response is fairly close to the first order, since the numerator terms almost cancel the smaller denominator terms. Plate 2 would slow a similar response at low and moderate frequency, but the plate lag approach 0 at high frequency. Now we discuss about the second one topic of this lecture, that means predicting the behavior of control system. So the success of feedback control system is compensating for load changes depending on both on the element in the closed loop and one on the transfer function for the load changes. Because of the fluid flow legs depend on the number of plates between the sample point and the flow change, the critical frequency of the system is decreased by putting the sample point closer to the end of the flow. So we know that the critical frequency of system is decreased by putting the sample point close to the end of the flow. Sampling at the top plate for the reflux control or the bottom plate for the boilup control, that means in the last plate, boilup control also permit a high overall gain to be used, since the major concentration lag is about the same for the any control point. So the advantage of sampling at the end of the column would be less pronounced for the boiling control than for the reflux control, since the vapor flow lag are smaller and may be negligible compared with the other leg in the control. So the possible advantage of the sampling near the feed plate is that the changes in feed composition are detected sooner and corrective action can start before specification product result. So the computer study of the Rose and Williams and of the Brown show top plate control is much better than the intermediate plate control. However, the load change used in both studies was a simultaneous change in feed composition and feed. So this is the predicting the behavior of the control system. So in this lecture we discussed about the frequency response of column, and then after we discussed about the predicting the behavior of control system. So as per the GTU, this is the very important chapter. So many times the question asked like in this chapter, explain the frequency response of the column, then types of the leg, and also explain the control system in the distillation column like bottom composition control, then after top control, then both product composition control. These are the type of questions asked in the GTU exam in this chapter.